Welcome back to the Deep Dive, the place where we turn massive amounts of complicated information into crystal clear, high-impact insights. If you are prepping for a critical meeting, catching up on the cutting edge of modern AI, or just want to gain a thorough understanding of one of the most exciting transformations in healthcare, you are absolutely in the right place. Today, we are undertaking a deep dive into the systematic review of foundation models in medical image analysis. Let us start with the revolution we were talking about. Medical imaging. I'm talking about X-rays, CT scans, MRIs. It's the cornerstone of modern diagnosis. But this system is, well, it's straining. The diagnosis relies on manual interpretation, which is time-consuming, intensely labor-intensive, and, it's prone to high variability between different observers.
That's right.
Our sources confirm that as imaging techniques improve and create more complex multidimensional data, the burden on clinical staff just increases dramatically.
That sets the stage perfectly. For the last decade, we have relied on traditional deep learning, or DL, to provide some relief. But these models were narrow specialists. They could achieve superhuman accuracy on one specific task, say, classifying breast cancer in mammograms or segmenting the liver.
Right. They were phenomenal specialists, but they created a massive scalability problem. To train these specialist DL models, you needed an enormous amount of annotated data for every single task.
Exactly.
You wanted to segment the spleen, thousands of hand-labeled spleen scans. You wanted to detect a specific kind of cardiac device.
You had to start the labeling process all over again.
It was just unsustainable.
It was. Labeling requires highly trained clinical experts, making the process labor-intensive and incredibly expensive. Foundation models, or FMs, have completely changed the calculus here. They're the generalists of the AI world.
So let us define FMs clearly for you, the learner. They are the new architecture, the new paradigm. They are trained on massive, diverse, and crucially, often unlabeled datasets. They learn what the source calls generalized representations.
And that generalization is the absolute key to the revolution. Because they've learned from such a vast, heterogeneous pool of data, they are characterized by their ability to adapt to a wide range of downstream tasks. They use what's called zero-shot or few-shot adaptation.
Okay, so think of traditional DL as hiring a locksmith for every single lock in your house. FMs are the master key, capable of performing a new task like segmenting an organ they have never explicitly been trained on with minimal or no additional fine-tuning.
And that efficiency is the massive leap forward.
Okay, let us unpack this. What exactly makes these models so foundational, and how do they overcome the fundamental limitations that traditional specialist AI faced?
Well, they achieve this by moving from being narrow specialists to broad generalists. We're going to explore two main categories today.
Yeah.
Vision-only models, or VFMs, which focus on processing image data for tasks like segmentation or classification, and then the vision language models, or VLFMs. These are even more sophisticated. They jointly embed visual data with text reports to enable complex diagnostic reasoning.
So the mission is clear.
The mission is clear. Large-scale pre-training using mountains of unlabeled data, followed by minimal adaptation to specific clinical tasks.
To truly appreciate the scale of this change, we have to look under the hood at the architectural shift. We started with the giants of the last decade, convolutional neural networks, or CNNs.
That is correct. The CNN era, with models like VGGNet and ResNet, absolutely dominated medical image analysis. They were powerful, and they were the first models that could seriously challenge human accuracy in specific, highly defined tasks.
And ResNet was a big deal.
ResNet was pivotal. It introduced residual connections, essentially shortcuts, to solve the vanishing gradient problem, which allowed us to build much deeper networks without the training signal just dying out.
Hang on, for those of us who have not touched a linear algebra textbook in a while, what does the vanishing gradient problem actually prevent? Why was ResNet's shortcut so revolutionary?
That's a great question. Imagine you are building a vast, multi-story factory. When you train a deep neural network, the error signal, the gradient, has to travel all the way back from the final layer to the first layer to update the weights.
Okay.
In very deep, traditional networks, that signal would get smaller and smaller as it moved backward. It would vanish.
So the first few layers just stop learning.
They stop learning entirely. The early layers, which learn the most foundational features like edges and textures, just stagnate. ResNet's residual connections allowed that error signal to bypass intermediate layers, ensuring the core knowledge layers at the bottom of the network continued to receive a strong update signal.
It made deep learning actually possible.
That's it.
That makes the UNet architecture, which is still incredibly relevant, even more impressive, given it predates some of these deeper ResNets.
UNet is foundational in medical segmentation for a reason. Its unique encoder-decoder design was perfectly suited for localization.
So the encoder part compresses the image.
Right? It compresses the image to capture high-level semantic features, what is in the image. Then the decoder expands it again to recover the spatial resolution.
To figure out where exactly that structure is located.
Exactly.
And the genius of the UNet design lies in its skip connections.
Absolutely. The skip connections are the structural brilliance. They bridge the early high-resolution feature maps from the encoder directly to the decoder.
And that preserves the fine-grained spatial features.
It does. Without them, the decoder would have to rebuild the boundaries and shapes from scratch, leading to blurry or inaccurate segmentation masks.
In medical imaging, where precision segmentation of a tumor boundary or an anatomical structure is non-negotiable, those skip connections are essential.
Absolutely essential.
Yeah.
And later iterations, like VNet, simply adapted this idea for 3D volumetric data using 3D convolutions.
But despite their dominance, the sources point out an inherent limitation in the CNN structure that ultimately capped its scalability.
That limitation is the localized nature of the convolutional filter. A filter only sees a tiny local region of the image at any one time.
So it's like looking at a vast mural through a microscope.
That's a perfect analogy.
Huh.
They are brilliant at capturing local features, edges, textures, but it becomes computationally prohibitive for them to model long-range dependencies.
For instance, how a lesion in the lung relates to the position of the diaphragm.
Exactly. That local focus limited their ability to generalize widely.
And that is the vacuum filled by the transformer, an architecture stolen directly from natural language processing.
The vision transformer, or VIT, is the true paradigm shift. The core conceptual trick is simple, but profound. They stopped treating images like 2D grids and started treating them as sequences of fixed-size, non-overlapping patches.
Essentially like word tokens in a sentence.
Precisely.
So whether it is a chest X-ray or a gigapixel pathology slide, the image is first sliced into chunks.
Exactly, and those chunks are processed by the self-attention mechanism. This is the real power source of the FM revolution.
So instead of a localized filter.
Instead of a localized filter, the attention mechanism models global interactions. Every patch token is allowed to talk to and weight the importance of every other patch token across the entire image.
And that enables VITs to capture those crucial long-range contextual relationships.
It does, and it flexibly adjusts its receptive fields based on the input data. It is the difference between the CNN microscope and the transformer's panoramic view of the entire clinical landscape.
This allows the model to see not just the tiny lesion, but how that lesion fits into the overall anatomical context of the patient, regardless of its position in the image.
That's right.
We are seeing major architectures like Swin transformers and UNetter, which use this principle, become foundational for high-resolution anatomical segmentation.
Their scalability catalyzed the development of true generalists, like the promptable segment, anything model SAM, and universal models like total segmentator, which aim to segment dozens of structures from diverse modalities using a single attention-based backbone.
So if the transformer is so superior at global context, why do we still bother with the CNN? We see a lot of hybrid models cited, combining the two. Is it just speed, or is the CNN doing something the transformer simply can't yet?
It is both speed and efficiency in a specific task. CNNs are incredibly efficient at those initial low-level local feature extractions. The pure VIT, while powerful, can sometimes be, computationally heavy, especially at the highest resolutions.
So hybrid architectures combine the strengths?
They do. They integrate a CNN backbone for efficient local feature extraction with transformer layers to then capture that crucial, unifying global context.
Like having a team of expert local surveyors, the CNNs, feeding data to a master cartographer, the transformer.
Precisely. Medformer is a key example cited, combining a CNN backbone with VITs for localized attention and improved global efficiency across complex medical tasks. This convergence leverages the strength of locality while overcoming its dependency limitations, resulting in architectures that are both efficient and generalizable, the perfect balance for resource-intensive clinical settings.
So we have established that the transformer architecture can handle the inherent complexity and massive resolution of clinical images, but that just creates an even bigger appetite for data. Since labeling is virtually impossible at the scale required, we are talking billions of data points. How do we feed this architectural beast?
And that's where the real magic comes in.
Self-supervised learning, or SSL.
SSL is the single greatest efficiency hack in modern medical AI. It is the core foundational paradigm because it unlocks the 99% of previously useless, unlabeled data.
So instead of relying on human annotators,
The SSL models generate their own supervisory signals, their own pseudo-labels, directly from the data itself.
it is the ultimate form of automated learning. It is like training an expert by forcing them to solve complex puzzles and internalize the patterns, rather than simply memorizing flashcards labeled by someone else.
That is an excellent way to put it. We can categorize SSL into three key techniques, starting with predictive learning, where the model predicts a masked or transformed aspect of the data.
What are the concrete clinical examples of how we transform medical data to create these puzzles?
Well, early examples that informed the medical field included relative patch prediction. The model takes two image patches and predicts one patch's spatial position relative to the other. This forces the model to learn the spatial dependencies, how anatomical structures connect.
I see. And then there's the jigsaw puzzle task.
Right. Shuffled patches are given, and the model predicts the correct permutation. This is highly effective at capturing semantic and spatial context.
I noticed in the review that rotation prediction, a common predictive task in general computer vision, is explicitly deemed unsuitable for medical images. Why is that specific transformation often avoided in the clinic?
That is a really important detail that reflects domain specificity. Natural images can be rotated and still retain, meaning a dog is a dog, no matter which way it faces.
But a chest X-ray has a top and a bottom.
Exactly. Medical images have fixed anatomical orientations that are clinically standardized. Rotating a chest X-ray 90 degrees fundamentally violates that standard and changes the clinical interpretation relative to the patient's body orientation.
So any task that encourages the model to be invariant to orientation is actually detrimental to medical application.
Detrimental, yes.
That distinction highlights how different medical AI is from general AI. Okay, moving on to generative learning, which feels like the most intuitive way to learn context. This is what we see in NLP with masked language modeling.
Yes, that translates to masked image modeling, or MIMA, in vision. The concept is elegant. You utilize the input data itself as the supervisory signal. You mask out large portions of the input image, say 75% of a CT slice, and the model must reconstruct the missing information.
And this compels the encoder to learn incredibly compact, informative, and structurally coherent representations of the anatomy.
It has to, in order to fill in the blanks plausibly.
And the most cited example here is the masked autoencoder, or MAE.
MAE uses a VIT encoder-decoder architecture specifically to reconstruct those missing regions. It is highly efficient because the encoder only processes the visible, non-masked patches.
And for our field, there's VISMAE.
Yes, an essential adaptation. VISMAE extends this reconstruction concept to volumetric medical data, proving that this self-supervision works effectively for 3D classification and segmentation tasks. And beyond that, in the vision language FMs, we see masked representation modeling, where models like RedFM train on simultaneously masked image and text data to generate coherent radiology reports.
And if meme is powerful, diffusion models feel like they are leading the next frontier in generative learning. They are all over the news for creating art, but how are they impacting medical image analysis?
Diffusion models are powerful generative frameworks, and they are gaining serious traction precisely because they offer high-fidelity generation. The concept is learning to reverse a gradual process of adding noise. MedFM is a critical example. It learns to reverse that noise process to generate high-quality medical images.
What is the clinical application of generating a synthetic image? Is it just for pretty pictures?
Not at all. Its utility is massive. First, it supports image denoising and artifact removal without needing explicit training data for those tasks.
Okay, that's useful.
Second, it allows for anomaly detection by training the model only on healthy images, and anything that requires too much effort to reconstruct is flagged as an anomaly.
But the big one is image synthesis.
Most powerfully, yes. It enables image synthesis. This allows researchers to generate highly realistic, clinically accurate synthetic training data.
Which overcomes data scarcity before the segmentation or classification task even begins. You're essentially expanding the training set without relying on real patient data.
Exactly. It's a phenomenal ability to circumvent the primary bottleneck of medical AI.
Finally, let us cover contrastive learning, which seems to be the engine behind many of the most famous generalist models.
Contrastive learning is a discriminative technique. It teaches the model to separate what is the same from what is different. It trains the model to map positive pairs, so augmented versions of the same image closer together in the embedding space.
And at the same time, it pushes negative pairs, different images, farther apart.
Right. The model learns representations that are invariant to minor changes, like contrast or cropping, but discriminative between distinct clinical samples.
SimCLR seems to be the first major architecture here, but it was resource hungry.
It was. SimCLR relied on strong data augmentation, but required huge batch sizes, hundreds or thousands of images processed simultaneously, to ensure a diverse set of negative samples within that batch.
And that made training computationally expensive and memory intensive.
It restricted accessibility. MoCo, or momentum contrast, solved this hardware limitation by maintaining a dynamic queue of negative samples from previous batches.
Which significantly reduced the memory cost.
Yes, while achieving similar performance. It decoupled the need for massive batch size from the need for a massive number of negative examples.
And then we have the Dino family, which took a different route by seemingly avoiding the need for explicit negative pairs altogether. That sounds like a major step forward.
It is genuinely mind-boggling how quickly the field iterates. Dino 2, and Dino 3 use a self-distillation strategy. It is a teacher-student framework.
A teacher-student framework.
Think of the teacher network as a grizzled veteran whose wisdom, the optimized weights, is shared with the younger student network. The teacher network's weights are momentum updated, meaning they change very slowly and are highly stable. This provides a consistent, high-quality target for the student to learn from.
So the student learns from the stable, reliable expert, ensuring it learns the right way without being distracted by noisy or unnecessary data.
Exactly. And that eliminates the need for complex management of negative pairs.
Which enables the emergence of extremely rich, semantically meaningful features.
And robust cross-domain generalization. Dino v3 even integrates something called gram anchoring to stabilize the dense feature maps during pre-training, further enhancing the model's ability to transfer knowledge.
Before we jump to multimodal models, we briefly need to touch on semi-supervised learning, which feels like the natural compromise for the medical sector.
Semi-SL is incredibly practical in the medical domain. It bridges the gap by leveraging the small, scarce set of high-quality labeled data that we do have, alongside the vast corpus of unlabeled data.
Which is perfect for when annotations are expensive and inconsistent.
Ideal. Strategies like consistency regularization, where the model's predictions should be consistent, even if the input is slightly augmented, and pseudo-labeling are key. Models like FixMatch use high-confidence predictions on unlabeled data to generate those pseudo-labels, guiding further training and proving highly effective for classification and segmentation when manual labels are severely limited.
Now we enter the specialized world of vision-only foundation models, exemplified by the segment anything model, or SAM. When Meta AI released this in 2023, it introduced the concept of universal segmentation to the general public.
SAM is a monumental achievement for generalization in computer vision. Its architecture, relying on a VIT image encoder and a prompt encoder feeding a lightweight mask decoder. It just demonstrated exceptional zero-shot segmentation capabilities.
All guided by simple prompts points, bounding boxes, or text.
And it was trained on over 1 billion natural image masks.
But the immediate challenge when researchers tried to bring it to the clinic was what is called the substantial domain gap.
That is the medical hurdle. Natural images have clear boundaries, distinct textures, and consistent lighting. Medical images, CTs, MRIs, are highly complex.
They deal with fluid-filled structures, fuzzy boundaries, low contrast.
And complex, heterogeneous anatomical layouts.
Yep.
So directly applying SAM, which was trained on pictures of cats and cars, often resulted in suboptimal, inconsistent segmentations.
So the first wave of research focused on bridging that gap by fine-tuning.
The initial approach was brute force data adaptation. MedSAM utilized 1 million medical image mask pairs across diverse modalities like CT, MRI, and ultrasound for fine-tuning. This demonstrated that the SAM architecture could learn medical semantics if it was grounded in enough medical data.
And SAM Med2D scaled this even further.
It did, fine-tuning on approximately 4.6 million 2D medical images and nearly 20 million corresponding masks, achieving significantly superior accuracy over the original generalist model.
But fine-tuning the entire multi-billion parameter model is a massive undertaking, computationally. We quickly saw the push toward efficiency become paramount.
That is where parameter-efficient fine-tuning, or PEF, entered the medical lexicon. SAM adopted PFT via LoRa, or low-rank adaptation, layers.
How does LoRa work?
LoRa works by freezing most of the original model's weights and only training small, highly specialized adapter layers. This technique achieves comparable segmentation accuracy to full fine-tuning methods while significantly reducing both the required data and the GPU memory footprint.
So instead of needing a data center to adapt the model, you can run the adaptation on much more accessible hardware, democratizing the technology.
Exactly, and the drive for efficiency continues, moving toward deployment in resource-constrained clinical settings. We are seeing lightweight variants like Swift MedFam and MedFastSam.
Which compress the architecture.
Right. MedFastSam reduced the parameter count to just 15% of the original SAM. And even more practically relevant are models like RapidMedSam, which replace the standard encoder with CNN-based backbones like RapidVT, specifically optimized for CPU inference.
Enabling low latency segmentation on standard clinical workstations without specialized expensive GPUs.
Absolutely. It immediately removes a massive economic barrier to clinical adoption globally.
However, moving beyond 2D, medical images are inherently 3D CTs and MRIs are volumetric. Why is naively applying 2D SAM slice by slice suboptimal?
It is the volumetric challenge. Applying 2D SAM slice by slice fundamentally ignores the continuity and relationships between the slices, the interslice dependencies.
Which leads to segmentations that are inconsistent or even nonsensical when you look at them in a 3D reconstruction.
Exactly. Solutions involved migrating to full 3D architectures, such as SAMED 3D, which introduced 3D patch-based encoders. Other models, like MedSam2 and Memorizing SAM, creatively treated 3D segmentation as a video object tracking problem, leveraging the temporal continuity between slices to achieve more coherent, accurate results across the entire volume.
SAM is fundamentally reliant on a prompt, meaning a human has to tell it what to segment. The next logical step, then, is to automate that prompting process entirely.
That is the new paradigm: prompt optimization and automation. Manual prompting is just too slow for a clinical workflow. AutoSAM introduced a fully automated pipeline using a trainable feature extraction module to infer prompts directly from the image data.
Hybrid approaches are also popular.
Very, integrating tools like YOLAV8 to generate highly precise spatial prompts. We also see sophisticated refinement loops, like RFMedSam2, which uses a quick initial unit prediction to generate a preliminary mask.
And that mask then serves as an automated, high-quality prompt for a multi-stage refinement pipeline.
That's it?
And the most fascinating convergence is the use of a large language model to guide the segmentation. Tell us about Zeus.
Zeus takes the concept of zero-shot guidance to its extreme. It uses an LLM to analyze the input image and generate natural language instructions that act as the segmentation prompt.
So a clinician could type, segment the upper lobe of the left lung showing signs of fibrosis.
And the LLM processes that instruction and generates the necessary spatial prompts to guide the VE encoder. This demonstrates the powerful future, where we blur the lines between vision and language for highly anatomically grounded tasks.
SAM is just one example of VFMs. We need to look at other generalist vision models designed for end-to-end task-agnostic use that are not prompt-based.
These are the universal segmentation backbones. Total Segmentator, for example, is a dedicated 3D NAU's NetCNN backbone that segments an astounding 104 anatomical structures in CT scans simultaneously.
Yep.
And SegVol, inspired by SAM but designed for 3D, incorporates a CIP-based text encoder to segment over 200 structures across CT and MRI.
The goal here is complete anatomical mapping from a single forward pass.
Exactly.
VFMs are also transforming high-level classification and diagnosis.
They're learning powerful semantic representations. Look at ophthalmology. RedFound is a pioneering FM trained using masked autoencoding on 1.6 million unlabeled retinal images. It learns ultra-fine-grained anatomical features and can be adapted rapidly for downstream tasks, like detecting early diabetic retinopathy or grading glaucoma.
But it often surpasses models trained specifically on labeled data for those tasks.
It does. The generalization is exceptional.
And in general radiology.
CheckFound uses a VIT backbone trained on nearly 1 million chest x-rays. This large-scale, label-free pre-training allows it to learn rich representations of the entire thoracic anatomy. It supports diverse tasks, from cardiovascular risk prediction based on subtle cardiomegaly to detecting mispositioned central lines or other medical devices.
And what about pathology with those gigapixel whole slide images?
For that, ProvGigapath is key. It uses DynoV2 pre-training combined with long-net modeling to handle those massive images, achieving state-of-the-art results in cancer subtyping and mutation prediction.
These FMs are supporting the entire clinical workflow, even foundational tasks like registration and synthesis.
Absolutely. Tasks like image registration aligning scans taken at different times or with different modalities are critical. Unigraticon is a registration FM pre-trained on multi-anatomy, multimodality data.
Which enables robust zero-shot generalization for aligning diverse scans.
Yes. And on the generative side, MAALM employs a three-stage diffusion framework to generate high-fidelity 3D CT volumes. And SynthFM is specifically designed to generate anatomically realistic synthetic data for training other segmentation FMs, creating a continuous loop of data generation to alleviate scarcity without relying on real patient data.
We established that clinical data is inherently multimodal, the image plus the accompanying radiological report or clinical notes. VFMs handle the visual data, but VLFMs are where the complex diagnostic reasoning starts.
Right, because they merge the text and the image.
This is the emergence of true clinical intelligence.
It is. VLFMs jointly embed visual and textual modalities. The core architecture is typically a dual encoder system, a vision encoder, and a text encoder trained using contrast of loss. This process aligns image features with text semantics into a shared latent space.
But the challenge of alignment in the medical field must be orders of magnitude harder than aligning a natural image with a general caption. It is not just about general similarity.
No, it is about aligning a tiny localized visual cue, say, a small nodule, with a specific, nuanced sentence deep within a long report.
That is the essence of the fine-grained alignment problem.
Exactly. General models like CLIP fail because they lack medical specificity. Gloria addressed this by introducing a dual contrast of loss, learning joint global, the whole image in the whole report, and local alignments.
What are local alignments?
Specific regions and specific text tokens. Asibsa further refined this by focusing specifically on aligning clinically significant regions with corresponding text entities. This moves the alignment from broad concepts to precise clinical detail.
Since huge, high-quality paired image report datasets are rare, how do these VLFMs overcome data scarcity? They must leverage external knowledge.
They absolutely do. PMC CLAP built a massive dataset of 1.6 million image caption pairs extracted from PubMed Central articles, essentially repurposing public scientific literature for training.
And MedSalab.
MedSicLipe used a knowledge-infused semantic matching loss, incorporating external medical ontologies like MetaMap to resolve ambiguity and align features more accurately based on professional medical terminology.
And TrekZero used an extremely clever pre-training approach to avoid paired data altogether.
TrekZero implemented a decoupled pre-training paradigm. It first trained the vision encoder on huge amounts of unlabeled images using SSL.
Okay.
Then it aligned those visual features not with reports, but with structured disease embeddings derived from bioclinical BERT. This avoids relying on those scarce paired image-labeled datasets entirely.
It uses expert language knowledge to guide the vision system.
That's right.
We are seeing a critical shift. Models are moving from just handling data efficiently to explicitly incorporating medical expertise or domain knowledge right into the training structure.
These are the knowledge-enhanced VLFMs. MedCLAP is a prime example. It extracts semantic triplets entity, position, and existence from radiology reports, and crucially, enriches these with semantic descriptions from external knowledge bases. This enhanced data serves as context for the Fusion module, directly resolving clinical semantic ambiguity.
And ARL does something similar.
ARL similarly integrates Unified Medical Language System, or UMLS-based medical knowledge during pre-training.
And SAT, the segment anything with text model, also leveraged knowledge enhancement specifically for anatomical segmentation.
SAT incorporated a structured anatomy knowledge tree containing over 6,500 anatomical terms directly into its text encoder. This ensures that when the model receives a text prompt like segment the apex of the heart, the model reasons based on anatomically grounded concepts, not just statistical pixel patterns.
It is anatomically aware segmentation.
Yes, exactly.
The ultimate goal of VLFMs, though, is to move beyond retrieval and classification toward free-form reasoning and generation, which leads us to generative VLFMs.
Generative VLFMs are designed to produce high-level outputs.
Yeah.
Automated radiology reports, complex diagnostic summaries, and conversational answers. These models typically extend robust large language models, Llama, Quen, Vicuna, with specialized vision encoders.
To create multimodal reasoning engines.
Right.
Tell us about the key examples of automated report generation.
RADFM is a visually conditioned autoregressive text generator that supports all major 2D and 3D modalities, including X-ray, CT, MRI, and PT. Its primary goal is automated report generation and diagnosis.
But here's the critical clinical risk. Hallucination, the AI making up medical facts.
And preventing the AI from making up medical facts is an existential necessity in the clinic.
So how are models mitigating this?
Lingshu is a prime example of proactive mitigation. It employed multi-stage training combined with reinforcement learning using verifiable rewards, or RLVR. This system rewards the model not just for sounding plausible, but for generating statements that can be empirically verified against established clinical knowledge or the image itself.
So this engineering is specifically designed to enhance clinical reasoning and reduce that catastrophic risk.
Exactly.
Another key system is Chexigent.
Chexigent is an instruction-tuned VLFM specifically designed for chest X-ray interpretation. It was trained on an immense dataset of 6 million CXR text QA triplets, setting a new benchmark for fine-grained interpretation tasks.
And this demonstrates the power of supervised tuning after large-scale pre-training.
It does.
And the newest generation, the interactive systems, seems poised to transform the clinician's interface entirely, moving the AI from background processing to a collaborative partner.
Interactive VLFMs function as intelligent clinical assistants. ElvaMed is a key model here, adapted for conversational assistant tasks in biomedical imaging. It allows clinicians to query the images using natural language, quote, "Is this finding consistent with pneumonia?" and receive detailed dialogue-driven diagnostic reasoning.
It essentially moves the AI from a simple tool to a collaborative consultant.
Precisely.
This systematic review included a meta-analysis, and the resulting quantitative trends highlight just how explosively fast this field is moving.
The publication surge is undeniable. The data shows exponential growth in both VFM and VLFM publications, beginning sharply around 2021 and continuing through 2025. This explosion directly correlates with the release of large, generalist pre-training frameworks like CLAP and SAM, and the growing accessibility of public medical datasets.
Looking at the data itself, there's a clear reliance on public datasets. What does that tell us?
It shows that resource sharing is driving the FM revolution. Over 60% of all studies for both VFM and VLFM rely on public data. For VFMs, CT data is the largest source, with abdominal and whole body segmentation datasets like AMOS and Total Segmentator being dominant.
And for VLFMs?
For VLFMs, the reliance is absolutely paramount on chest X-ray data from corpora like MIM, CCXR, and Chexpert. This pivotal reliance suggests that these specific public datasets are literally defining the foundational knowledge base of medical AI today.
And how are the actual tasks changing over time?
For VFMs, segmentation remains the undisputed dominant task. But in VLFMs, we see a crucial maturation. Early studies focused on basic classification or image text retrieval.
Okay.
However, studies from 2023 onward show a significant increase in advanced tasks: report generation, visual question answering VQA, and complex clinical reasoning.
This demonstrates the field is shifting from simple pattern matching to vision-language-guided diagnostic and predictive modeling.
That's right.
Speaking of complexity, the review also analyzed the training objectives, finding a statistical trend towards significantly more complex loss functions.
That is a direct reflection of the sophistication required to handle multimodal data. Modern VLFMs rarely use a single objective. They're moving toward multi-objective frameworks, integrating complementary losses like contrastive loss for alignment, cross-entropy loss for classification, and masked modeling loss for generation.
And this multi-objective learning is necessary to achieve robust multimodal representation.
And to reflect the complex nature of clinical reasoning.
Now let us address the critical deployment question. Universal versus specialist FMs. Does the clinic need one master key that works okay on every lock, or hundreds of perfectly crafted specialized keys?
This is the core trade-off. Universal FMs, like MedSam, emphasize breadth and generalization across modalities and tasks, relying on weak supervision.
The pro being they are invaluable when labeled data is scarce. They provide a strong starting point.
Right. The con is that their breadth complicates clinical validation and regulatory approval because performance can vary wildly across different clinical sites, and they can lack the sensitivity needed for highly specialized, domain-specific nuances.
Specialist FMs, then, are the deep experts.
Specialist FMs, such as PFound for ophthalmology, are designed with tailored architectures and datasets for specific contexts. They typically use high-quality, expert-annotated data to achieve higher interpretability.
And guaranteed performance consistency.
Exactly, and a more streamlined regulatory pathway. The con, of course, is that they have narrow applicability.
The sources suggest the field is converging on the best of both worlds' hybrid solutions.
That is the pragmatic convergence point. Hybrid strategies leverage universal power with specialized precision. You pre-train a universal backbone on massive, heterogeneous data to learn general concepts.
And then adapt it to specialist domains using lightweight mechanisms like PEFT-LoRa or modular adapters.
Yes, Unimedcli, for instance, extends universal embeddings by adding expert-aware projection layers, allowing the generalized knowledge to be efficiently fine-tuned for a specific hospital or pathology.
Moving beyond simple accuracy scores, how should FMs be rigorously evaluated to ensure they are trustworthy enough for a doctor to rely on?
The evaluation must be multifaceted. First, we need representation evaluation, assessing the quality of the embedded features the model learns. This includes cross-modal similarity, using metrics like recall at K to test how well image-to-text retrieval works.
And linear separability.
Yes, tested via linear probing training, a simple classifier on the frozen embeddings to measure their inherent discriminative strength.
Then there is robustness evaluation, which is essential for real-world deployment across diverse hospital systems.
Trustworthy FMs must be stable under distribution shifts. Cross-domain testing is absolutely crucial here, validating performance across different variables that were not in the training set.
Like different scanner manufacturers, Siemens versus GE, or different imaging protocols.
Or different institutions globally. CTCLAP, for example, validates its zero-shot performance using external cohorts to prove its robustness to shifts in data acquisition. We also need long-tail evaluation, ensuring the model reliably recognizes rare conditions or subtle abnormalities, which is usually measured using per-class metrics.
And the most important metric for a clinician is interpretability. If the AI cannot explain its reasoning, the diagnosis is practically unauditable.
Interpretability evaluation must anchor the AI's reasoning to clinical reality. We rely on three key strategies. First, regionality grounding.
So, anchoring predictions to specific anatomical or pathological regions, not just broad heat maps.
Exactly. Models like GKMVLP, which leverage medical knowledge aligned with anatomical regions, transform interpretability from a subjective visualization into a quantifiable localization metric.
And providing case-based justification must be a massive aid to the doctor's trust.
It is essential for auditability. Retrieval-based evidence involves allowing clinicians to audit a prediction by retrieving similar cases or reports from the latent space that inform the AI's current decision.
So the AI flags a lung nodule, and the clinician can instantly ask, "Show me the 5 most similar cases you used to make this prediction."
And that shifts the AI from a black box to a collaborative system based on shared evidence. While saliency maps like GradCam are still qualitative benchmarks, the source emphasizes they must be paired with region-level scores or retrieval evidence to ensure reproducibility.
Finally, the systematic review we analyzed highlights the crucial imperative of ensuring fairness and equity in the data itself.
This is a critical challenge documented in the research. FMs are designed to generalize, but they inherit and amplify demographic and geographic biases present in their massive training datasets.
And the meta-analysis shows a significant skew.
A significant skew in training data toward North America, Europe, and East Asia, severely underrepresenting Global South populations and diverse demographic cohorts.
What is the risk of this data skew?
It restricts generalizability. The model might perform perfectly on a scanner made by Siemens in Boston, but fail catastrophically on a different scanner protocol in rural India simply because it never encountered that variation in training.
So this risk of unequal performance across demographics and geographies is not just an ethical issue.
It is a clinical failure that could widen existing health equity gaps. The review explicitly mentions that effective mitigation must span the entire FM lifecycle. During training, researchers are exploring techniques like adversarial debiasing, which embeds fairness constraints to prevent the model from learning correlations based on sensitive attributes like age or race.
And post-deployment, continuous monitoring is non-negotiable.
Absolutely.
And this data imbalance has regulatory ramifications too.
It does. The EU AI Act, for instance, classifies medical AI systems, including FMs, as high risk. This legally mandates fairness, transparency, and accountability as non-negotiable requirements for clinical translation.
So researchers must now rigorously evaluate the utility fairness trade-off using specialized group and individual fairness metrics before deployment.
It's a requirement.
This has been an absolutely colossal deep dive into a transformative field.
Indeed. We've moved from the inherent limitations of narrow, localized CNNs to the generalist power of transformer-based architectures, driven by the ingenious use of self-supervised learning to turn scarcity into massive data abundance.
We dove into the world of vision-only FMs, analyzing how promptable models like SAM are made clinically viable through efficiency hacks like LoRa and through automation systems like Zeus, bridging the domain gap into volumetric reality.
And we explored the cutting edge of vision language FMs, detailing how they align images with complex clinical reports, leverage external knowledge bases, and are evolving toward interactive generative systems designed to mitigate risks like AI hallucinations through verifiable reward systems.
The key takeaway for you, the learner, is this. Foundation models are decisively moving medical AI beyond simple pattern detection towards sophisticated diagnostic reasoning, visual question answering, report generation, and achieving a level of generalization that was previously impossible, making advanced AI collaboration a clinical reality right now.
This raises an important question. Given the significant computational and data requirements necessary to train and validate these universal foundation models, how can the global scientific community effectively decentralize FM development and monitoring to ensure that these powerful tools truly benefit all populations and institutions rather than remaining concentrated solely in high-resource research centers?
A question that must guide the research and infrastructure development of the next 5 years. Thank you for joining us for the deep dive.
Always a pleasure. We look forward to diving in again soon.